Okay, oxidation numbers are known as oxidation states, and it's a way of keeping track of electrons, okay? So you have to memorize the rules so that you can do more work later on. So here are the rules for oxidation numbers. Rule number 1, anytime you have an atom in its elemental form, it's going to have an oxidation number of 0. And I've given you a few examples. Pure sodium, that would have an oxidation number of 0. Pure oxygen, which you'll notice has a subscript 2 on it, which is totally acceptable because it's just oxygen. That also has an oxidation number of 0. P subscript 4, also elemental form of phosphorus, it would have an oxidation number of 0. If you had sulfur with a subscript 8 on it, that would also have an oxidation number of 0 because it's in its elemental form. So here you should make a note that it's fine if you have a subscript on it, but you cannot have a charge on the paper. Otherwise, it's not an elemental form. The next rule, a monoatomic ion has an oxidation number that is the same as its charge. Now, the charge has to be written on the paper, and there may not be subscripts in this case. So make a note of it. No subscripts, but you have to have a charge on the paper. So here I gave you some examples. K plus 1. So your oxidation number would be the same as the charge on potassium, which is the +1. Ca plus 2, the oxidation number would be +2. Cl minus 1, the oxidation number would be -1. Rule number 3, oxygen almost always has an oxidation number of -2, which is the same as its charge, which makes it easy to remember, except when you have peroxide, peroxide is O2 -2, so it's O subscript 2, and then it has a -2 charge in the upper right hand corner. Now peroxide has to be with a metal. It cannot be with a non-metal. So that means you have to know where the metals are on the periodic table. They're to the left of the stair step. So in this case, oxygen would have an oxidation number of -1 if it was peroxide, but that has to be with a metal. Or OF2. If oxygen is with F2, that means oxygen has a +2 oxidation state. Okay? I've given you some examples. H2O. You assign the oxidation number that you know. Well, in this case, oxygen would have an oxidation number of -2. Okay? In Na2O2, Na is a metal. So that means since you see O2 with a metal, you should be suspicious that this might be peroxide. So what I typically do is I assign the metal its oxidation number first. That way I can validate that this is peroxide. Well, sodium is a group 1A metal. Typically, group 1A metals have an oxidation number that is the same as its charge. So here, sodium would be a +1 oxidation number. That means this oxygen would have to be a -1 oxidation number, because one of the other rules that we're going to look at is the sum of the oxidation numbers in a neutral compound has to be 0. What that means is if I have 2 sodium at a +1, that's a +2 overall, and you're adding that to 2 oxygens at a -1, which is a -2 overall. So a +2 and a -2 add up to 0. And that makes sense. This is our neutral compound. Okay? For the next one, OF2, well, anytime you have oxygen with F2 in a compound, that means your oxygen is going to be a +2 oxidation number. So that means your fluorine must be a -1. And most of the time it is, because it's the most electronegative element, and the halogens tend to be -1s, okay? So a +2 combined with this -2 is going to add up to 0, and that makes sense for the oxidation numbers in a neutral compound to add up to 0. The next rule, hydrogen is almost always +1, which is the same as its charge on the periodic table, so that makes it easy to remember, except when hydrogen is with a metal, and they call this a metal hydride. When hydrogen is with a metal, it has an oxidation number of -1. So if you look at the examples that I've given you, we have H2O. Well, hydrogen here would be a +1. And if you have 2 hydrogen and a +1, then your oxygen must be -2, right? And that follows with the rule that we just read about in the third step for oxygen is typically a negative 2 for its oxidation number, which is the same as its charge. If you're looking at CaH2, Ca is a metal. This is a group 2A metal. Group 2A metals seem to have oxidation numbers that are the same as their charge. Therefore, calcium would be +2 for its oxidation number. Okay? If you have hydrogen with calcium, which is a metal, that means hydrogen must be -1. And it makes sense that it is, because if calcium is a +2 and you have 2 hydrogens at a -1, that makes this a -2 overall on the right side where the hydrogen is. A +2 and a -2 add up to 0. LiH. Lithium is a group 1A metal. That means its oxidation number is going to be the same as its charge, which is a +1. And since lithium is a metal, hydrogen has to be a -1, because this is hydrogen with a metal. We call these metal hydrides. That's when hydrogen has an oxidation number of -1. Okay, rule number 5. Oxidation states of compounds sum to 0. So I've been following this rule in the last couple of examples, and that means that if it's a neutral compound, that means there's no charge written on the paper. Okay, that means that your oxidation numbers have to add up to 0. So here, if I'm looking at CuCl, I'm going to assign the more electronegative element first, which is chlorine. It's in group 7A. They tend to be -1 for their oxidation numbers. If this is a -1, that means my copper must be a +1, because my oxidation numbers have to add up to 0. Rule number 6. Oxidation states of polyatomic ions, that means groups of elements. They have to have a charge written on the paper. That's a polyatomic ion. The sum of the oxidation numbers is the ion charge that's written on the paper. So if you have ClO3 -1, assign the oxygen first, because you know that it's usually a -2. By the way, if you have hydrogen and oxygen, or either one in a compound, you usually assign them first, because you know what they are. So if you have 3 oxygen at a -2, and we're trying to figure out what our chlorine is, well, our oxidation numbers should add up to this overall charge that's written, which is -1. So that means chlorine plus 3 oxygen at a -2 add up to -1. So chlorine plus 3 oxygen at a -2 add up to the overall charge of the polyatomic ion, which is written, and it's a -1. So you just solve for the unknown. This is Cl minus 6 equals -1. Chlorine is going to equal a +5. Okay. 7th rule. Assign the more electronegative element a negative oxidation number. So if you're looking at PF5, well, electronegativity increases up and to the right on the periodic table. Fluorine is the most electronegative element, so we will assign it its usual charge, which is a -1. We need to figure out what phosphorus would be. Well, phosphorus plus 5 fluorine at a -1 add up to 0, right? Phosphorus plus 5 fluorine at a -1 add up to 0, because there was no charge written on the board for that compound. It was neutral. So P minus 5 equals 0. P equals a +5. Last rule. Compounds containing more than 2 elements. You want to assign the element that's furthest to the right its most common oxidation state. Okay. Well, nitrogen is the furthest to the right here, so we're going to assign it a -3, because that's its most common oxidation state. Then from there, I would recommend assigning the more electronegative element between sulfur and carbon, which would be sulfur, its usual oxidation state, which is -2. That means we're going to calculate the oxidation number for carbon. So, -2 for sulfur, plus carbon, plus nitrogen at a -3 adds up to the overall charge on this polyatomic ion, which is -1, and that's written there on the example, okay? -2 plus -3 is going to be a -5. You're going to put the 5 on the other side. Carbon is going to be a +4. Okay? So the easiest way to get good at this is just to do problems over and over again. Remember, if you have hydrogen and oxygen in a compound, please assign them first. If you have multiple atoms, please assign the more electronegative element its oxidation number first. And if there is more than one oxidation state that could possibly exist for an element, assign the most common one.